Welcome to the session 2 of the unit 6 of our financial modeling course. In this session, we are going to consider estimation of risk. That is, we are going to estimate, or we are going to consider models that are used in estimating risk in financial modeling. By the end of this session, you should be able to do the following. You should be able to explain the difficulty of estimating the risk associated with asset returns. You should be able to state the basis of risk estimation models, explain the concept of heteroscedasticity, describe the various risk models and how they are specified, and explain the concept of volatility clustering. Estimating risk. In general, the variance or standard deviation is always used as a measure of risk, so we mostly quantify our risk in most descriptive analysis with the variance or the standard deviation. This can be done using actual historical price changes, or it can be an estimate of expected future volatility that is implied by option prices. So this is the point of the variability of the quantity which we are interested in. So for example, the variance or the standard deviation of the London Stock Exchange Composite Index is taken as a proxy for risk in the market, but it is based on the historical returns. Whilst in most estimation we are looking at the future, we always look forward. Therefore, estimating risk based on prior prices or previous prices will not be able to explain the actual reality or the real life phenomenon. How then do we find measure of risk for the future? Because if we are saying that the standard deviation depends or models or estimate risk for the past, then we should find a way to model risk for the future. So then we have to come away with some approaches. So the common approaches in finance which are used in estimating risk are the exponentially weighted moving average, which is simply ELMA. We have the autoregressive conditional heteroscedasticity or the ARCH model, and the generalized version of the ARCH model, or what we call the generalized autoregressive conditional heteroscedasticity. In our next session, we are going to consider these forward-looking estimation models for the risk of financial markets. The ELMA, or the exponentially weighted moving average model. This model is based on simple reasoning that is, events in the very past have remote influence on current events compared to recent events. The estimated exponentially weighted moving average models gives more weight to the much recent observation using an exponential scheme. So here we are saying that in the ELMA, or the exponentially weighted moving average models, when we are measuring risk, our focus is to give more weight to recent happenings more than previous or old issues or old happenings. So the ELMA model is stated as follows. That is, this is a measure of risk, which is the variance, and lambda as a parameter which is universal and has to be estimated and recorded for a particular market. So for instance, if we want to predict the GDP growth in the next quarter, we will consider the current GDP growth and perhaps that of the past 2 quarters, rather than considering the GDP growth for the past 10 years, because it is quite old. So as we earlier said, the ELMA mostly give weight to recent events compared to past events, or compared to events that are old enough. So the ELMA model has this estimation. This is how we estimate it, where this is the error term, or this is the error term, and the lambda is the measure of risk. As important as this model was, it also came across or came along with its own limitation, and that there was lack of universality or universal applicability of this lambda, which is a measure of risk, therefore making this model very difficult to be used outside its country of development. So there was a need for econometrician and other analysts to come across or to come along with different models that will help us in estimating risk. So in our next session, we are considering another development, that is the ARCH model by Robert F. Engel. The ARCH model. We earlier said that the pitfalls or the shortfalls of the exponential weighted moving average model was being improved or brought about the development of the ARCH model. So the ARCH model are similar to the exponential weighted moving average in modeling volatility, except that the autoregressive coefficients are estimated from the data instead of being held constant. So one will ask, what is the ARCH model? The ARCH simply has to do with autoregressive conditional heteroscedasticity. The ARCH model is a statistical model used to analyze volatility in a time series in order to forecast future volatility. In the financial world, ARCH modeling is used to estimate risk by providing a model of volatility that more closely resembles a real market phenomenon. The ARCH modeling shows that periods of high volatility are followed by even a higher volatility, and periods of low volatility are followed by lower volatility, a concept that we call the volatility clustering. In practice, this means that volatility or variance tend to cluster, which is useful to investors when considering the risk of holding or an asset over different time periods. The ARCH concept was developed by the economist Robert F. Engel in the 1980s. The ARCH immediately improved financial modeling, resulting in Engel winning the 2004 Nobel Memorial Prize in Economic Science. The ARCH model was designed to improve the econometric models by replacing assumption of constant volatility with conditional volatility. So, like the issue of the exponential weighted moving average, we earlier said that it had the perception that the error term or the volatility or the variance was constant, which is not actually the case in the real world. Therefore, the ARCH came to improve upon this, and it came with the idea of conditional heteroscedasticity or conditional volatility. Engel and his team working on ARCH model recognized that past financial data influence future data. So that is where the autoregressive component of the ARCH model came from. And the conditional heteroscedasticity part of the ARCH simply refers to the observable fact that volatility in financial market simply is constant. Thus, all financial data, whether stock markets or oil prices, market, the exchange rate or GDP, go through periods of high and low volatility. So according to Engel, this was developed in response to Milton Friedman's conjecture that it was the uncertainty about what the rate of inflation will be rather than the actual rate of inflation that negatively influence or impact an economy. So here the idea was not on the actual inflation but rather on the future or the probable inflation which comes across or which brings the idea of uncertainty. The ARCH model is in the form, this is variance, a measure of the risk, which is the ARCH model, where we have our omega, which is a constant parameter, and our alpha 1 multiplied by our alpha 1 multiplied by the error term of the previous day. So this is the squared error term, and the t minus 1 has to do with the last, which is the previous day, up to the alpha p multiplied by the error term of the last day in our observation. So the omega simply represents a constant parameter which should always be positive. It should not go to negative because it is a measure of volatility and we cannot have a negative volatility. Therefore, our constant parameter should always be positive. This represents the heteroscedasticity component where we have our alpha and the error term, and this should also not be less than 0. The omega we have already established that should not be less than 0, and the alpha term should be less than or greater than or equal to 0, so it should also not be negative. So it means none of the arch terms should be negative, because we are likely not to observe or to come across negative volatility. Therefore, the need for us to consider this or take this into consideration. So in modeling, we state this relation to include the returns equation and the error distribution. So that's for an arch model with normal errors. We state the model as follows, where RT is a return series and it's a product of the standard deviation and the error term, where our error term possesses the property of being independent and identically distributed with a mean of 0 and a constant variance. So the variance can now be also explained as I saw in our arch model. We are simply modeling the variance component of this series. So we are focusing on this component. So the constant variance is what we are focusing on, or what we are estimating in our arch model. Here we will build an arch model with lag 1, that is arch 1 model using the Ghana Stock Exchange Composite Index, which is the returns. I'm not going to use the price series because we have already established that the price series are not stationary. Therefore, the return series, which has been different, is the best data set for us to use in terms of any model. So the results are being shown in table 1, and you can see that these are the descriptive. We have the model volume, which is the arch model, the distribution, the method, among others. So we have also seen the information criterion which are being used to consider or to assess how the model fits the data. So we have the AIC, we have the BIC, among others. So the number of observations has been estimated to be 1548. As we saw that in the earlier submission, it was 1549, but after differencing, we are likely to have some elimination of the variables. Some of the data are being eliminated, so 1548. So the velocity model, which is our p-value, falls on 0.00, and this makes we have a coefficient of which is non-negative, actually non-negative, but it is quite insignificant. A standard error which is also quite insignificant, like the values are very small. The same thing with our p-value is 0.00, so our coefficient is 0.250. so this was the constant parameter, but the actual alpha 1 was the 0.250. Our t-statistics is actually less than 2. In most cases, we expect our t-statistics should be greater than 2, and so we will consider this model as in a way insignificant, but this will not be our focus in this session because we are likely to come across the significance of this model in our subsequent sessions. We earlier said that the standard deviation or the error term, that is the error term, should be normal with mean 0. So we are trying to verify this assumption. So it is clearly indicated that we have this assumption being met, as we have the mean being at the center. or the average being at the center, indicating that the residuals have been zero, or the average of the residuals are zero. So this, we have met the first assumption of the significance of the model. And also stationarity. So the standardized residuals are also in a way looks more stationary in a way. So there is some form of stationarity in the series. So we have also met the other criteria, as you can clearly see in this plot. And these are the plots of the conditional volatility. So we are simply plotting the parameters of the arch model. And in figure 3, that is the top diagram, shows that the errors have constant variance, and the bottom figure shows the evolution of volatility across time. So these are the constants or the stationary series. This shows that the residuals are stationary, and this also shows that this shows the evolving nature of the volatility across time. But we also have to establish that even though the arch model was of great importance in forecasting for risk in the financial market, there were some series of shortfalls that this model came across, where there was a need for development in this model. So the Boleslav in 1986 came across, or came up with a new model which were used, or which was a generalized form of the arch model, which we call the Gauge model, which was used in modeling risk as well, and mostly it has become the order of the day, unlike the arch model, because the arch model was facing series of problems with respect to estimation, as some estimation indicated that the arch was coming up with negative parameters, which was not the case, which was not part of its assumption. So in our next slide, we are going to consider the Gauge model. So we have now come to the Gauge model. That is the generalized autoregressive conditional heteroscedastic models. So simply, we are talking about the Gauge model being a generalization of the arch model of Robert F. Engel, and this was proposed by Tim Boleslav in 1986. The Gauge model was simply developed to improve or to cater for the issue of parsimony in the arch model. The Gauge model is a statistical model which is used in analyzing time series data where the variance or the error term is believed to be serially correlated. As in the arch model, we assume that the variance or the error term is not serially correlated, or it is not correlated. But in the arch term, it is only the squared error term is what we assume to be autocorrelated. But in the Gauge model, even when the series are autocorrelated, we can still forecast or model our estimation with the Gauge model. The Gauge model assumes that the variance of the error term follows an autoregressive moving average process. The Gauge model are used when the variance of the error term is not constant, thus the error term is heteroscedastic. Essentially, whenever there is the issue of heteroscedasticity, observations do not conform to a linear pattern. Instead, they tend to cluster. That is the issue of volatility clustering in time series data. Therefore, if statistical models that assume constant variance are used on this data, the conclusions and predictive value one can draw from the model will not be reliable. So the variance of the error term in the Gauge model is assumed to vary systematically, conditional on the average size of the error terms in the previous period. In other words, it has conditional heteroscedasticity, and the reason for the heteroscedasticity is that The error term is following an autoregressive moving average pattern. This means that it is a function of an average of its own previous lag or its own previous value or lag values. The gauge was, as we earlier said, was developed by Boleslav, and he was a doctoral student. That was the special part. He was a student of Robert F. Engel and a PhD student of Robert F. Engel, who sought to develop the arch model, which was developed by his supervisor based on the shortfalls of forecasting volatility in the asset prices of the arch model. This model rather assumed that the variations of returns was not constant over time, but they are autocorrelated as we have earlier submitted, or they depend on each other or dependent on each other. So for example, it could be observed that in the stock market, return series in periods of volatility tend to be clustered, or they tend to be dependent on each other. And also the main aim of the Gauge model was to bring about the issue of parsimony in the arch model. So we specify the Gauge 1-1 model. Well, this is the arch model and this is the Gauge model. Sometimes we use the word PQ, where the P is the arch model and Q is the Gauge model. And it simply has to do with the lags of the arch and the lags of the gauge, like we saw in our ARIMA model, where we have ARIMA 101, 20, 211, 212, among others. So similar to the arch model, we have our return series equal to the UT or U plus the ET, and the variance is being measured as the constant parameter plus the alpha multiplied by the previous value of the squared error term plus a parameter like the beta multiplied by the, so this is the arch term, this is the constant parameter, and this is the arch term, and this is the gauge term. So in the gauge we have an arch term and we have a gauge term, and the error term is being defined as we saw earlier. It has a constant variance or a variance which is equal to unity. It has a mean of 0. It is independent and identically distributed. In the model, variance at time t minus 1 fits into variance at time t. That's what we call the issue of being autoregressive and also autocorrelated. So we are saying that the previous value really influenced the current value in the gauge model, and even in the autocorrelated property of the gauge model, we are still able to model it, unlike the arch model, which had issues of such nature. So in this session, we have explained the difficulty of estimating the risk associated with asset returns. We have been able to state the basis of risk estimation. We've been able to explain the concept of heteroscedasticity as it applies to the issue of arch and gauge model. We have described the various risk models and how they are specified, and explained the concept of volatility clustering. Thank you for your attention as we meet the end of today's discussion. We hope to meet you once again in our next session.